Okay, so welcome to the third session in this series of data structures and algorithms, where we are still with the data structures, which is another very important data structure called as tree. And unlike your stack queue, this is going to be an hierarchical structure. You can see here the the tree, which is a natural tree where the root will be at the bottom. But in our data structure tree, the root will be at the top. So that's the only difference. But otherwise, it's all recursive. For example, you have many branches. That branch is a sub branch. That sub branch will have some more branches. So that's how here also it goes in our tree data structure. So what are we going to discuss today? These are the major topics that we'll be discussing. Basic definition. There are some repetitions here, slides, so probably I need to skip them. Some slides, though it looks similar, but actually additional information may be there. Just to make sure that, you don't need to recall, actually the same slide itself will get. So don't get, distracted by or wrongly understand that, okay, the same thing is repeating. Binary trees is the major topic of discussion. Of course, we do have general trees, but most of the operations which we are going to discuss will be on binary trees. So we'll try to understand the definition, major properties of these binary trees with examples. Then we have three traversal techniques that we'll be discussing. Traversal means how do you go through? See, if it's a linked list, you just have only one pointer to the header node, the first node, and using which you can actually go through all the nodes in the linked list. P equal to P of next. So you'll go to the next node, next node, next node. So you can put it in a while loop. You will be able to reach out to all the nodes in the linked list until you encounter the last node where the next field or the link field is null. Similarly here, we have to go through the tree for operation purposes or for simply printing what information we have or for some updation, anything. Basic operations on the data structure. So the way in which you go through the tree may be different from the linked list because it's or array. Array means index, direct A of 5. But here it's not so because it's a hierarchical structure. So how do you go in a hierarchical structure? It is something similar to, Google Map, you start from one, it's a network or a graph, but still assume that you have 3 paths in order to reach to my destination. So this is my destination, this is my source, right? So I can either take this route or this route or this route. Correct? So similarly here, I may have one node and the next level is this. So I can write like this. So starting from here, should I go here first or here or here? I mean, should I branch out in this fashion? I can go to this node first and then this and then this, or I can go so like this. There are possibilities. I'm talking about a general tree where you have any number of branches or subtrees. So all these concepts, the one which we are going to discuss. And how do we represent it? How do we store this entire tree in memory? Right? So there are two ways by which we can, this is one, this is two, implicit or vector. Another one is linked. Linked is very common. Vector also is useful for something like heap sort. which we'll see in the next session. So basically, what exactly we mean by a tree data structure, under which you have binary tree, the general tree. What is the definition again? These things. What are the properties of these tree structures, tree data structure, and then traversal techniques. We have three, I told you, in order, pre-order, and post-order. And of course, the two representations, linked and vector or implicit. So, and why we should talk about binary tree? Because of the implementation issues. If it's a general tree also we can, but there are some implementation issues. So binary tree is a hierarchical data structure consisting of nodes, similar to linked list. Each node has info field, but here it's left and the right. So don't confuse this with DLL, doubly linked list. Don't confuse that. There, doubly linked, you can go left, you can go right. That's all. It's not a hierarchical structure. And generally, there is only one pointer which points to the root node. So the topmost node in the entire tree structure. Something like, a company CEO is the topmost. College principal. We don't have two principals for a college, So we have one root for the entire tree from which you can go. Pointers, children nodes, subtrees, all these things we'll see in the figure in the subsequent slides. Just to give you some examples, where you can go through my another PPT, data structure applications. I've already uploaded to your Teams file tab, so you can go through that. Shortly, I'll be uploading a video corresponding to that as well in YouTube. So in case if you have difficulties, you can watch that video so that you will understand better about the real applications of certain data structures, especially arrays, stack, queue, circular queue, singly linked list, doubly linked list, circular link. Then, of course, trees, that. So directory tree now, Linux or Windows operating system. Folder, within that you have folders. That folder in turn has some folders, etc. Decision tree, which is very, very common in machine learning as well. Because one of the classification technique, decision tree is very famous, ID3 algorithm, Hunt's algorithm. These are very famous algorithms which are used to build the decision tree to make sure that you can take decisions, in the sense you can classify. For example, a patient, whether he is normal, he or she, or abnormal, whether the patient is normal or abnormal. How do you take the decision? Or a bank, whether to offer a loan or not. So yes or no. How do you take this decision? So you have a series of nodes which you should go through and finally get into this decision. Family tree, we know. Table of content, I already told you. So these are some of the tree terms. Okay, so yeah. So you have the topmost one, as I told you, it's the root node. See, this is a root node. And internal nodes are nothing but non-leaf nodes. External nodes are also called as, that means nodes without any children. You can see here. They don't have any children nodes. E, then G, H, D. Okay. A, of course, is an internal node. So these are external nodes. F is an internal, B is an internal, C is an internal node. Ancestors of the node, then depth. That means the height. For example, it might start from, I'll show you that in the next few slides. And height of the tree. So the We call this one as a level. So I can call this as level 0, this as level 1, this as level 2, this is level 3. If you start the root as 0, some people start root as 1 also, so it becomes 4. Basically, is the depth or the height of the tree. And it grows, you can see here in, it's a general tree. Remember, it's not a binary tree. I'll come to that binary tree next. And we also have a concept called as subtree. See, remember the definition of a tree is recursive. Okay. So what you see here as the main tree root, you have some children. Then again, for example, this is a subtree, shaded one. So for this may be root. And these are the children nodes. So this is a subtree, a small tree under this tree, like that. Then you can have the ADT with data. Of course, as usual, each node consists of the data and the left and the right link. I mean, if you have only at most two children which is being allowed. Otherwise, you have to have many links. So there are some generic methods which we can define for the ADT of the tree. That is size, is empty. Size means number of nodes maybe. Is empty whether the tree has elements or not. And it's an iterator where all elements you can think of. Positions, in order, pre-order is not mentioned here. That's what we are going to see later. So those are the major 3 functions which we need to add in this. Okay. Then you can access what is the position of the root parent or children given P, that is the root node address. And query whether it is an external node or an internal node, internal or external, then is it a root node? All these things, update, you can do it. There are copy, I mean, duplication kind of. So there are plenty of methods which we can actually define, but that runs into how many methods. So we have not listed all of them. So now coming to binary, why we should talk about only binary tree? Why not general tree? I leave it to you. As we proceed, we can also discuss that. So what is a binary tree? It's a data structure where each node has at most 2 children. You can have only 2 children, not more than that, but you can have less. You need not have any left or the right children, or you can have only 1 left or right. And you can actually have both, but not beyond 2. Okay, so here it's a simple binary tree where you have so many nodes, and you can see here no node has more than 2 children, and you have the left subtree and the right subtree. Okay, so with respect to the main tree root. So what is a general tree? General tree, there is no restriction that you can have at most 2 children. You can have any number of children, but only thing is these are all disjoint sets. For example, I can have T1, T2, up to Tn, right? There is no limit that, okay, we should have only 5 or only 4, etc. So that's why the implementation becomes a little difficult, especially in C language, when you define a self-referential structure. Now, since this also is dynamic, you cannot. But as binary tree, you can define only 2, left and the right link, correct? Because here each node, you can have n number of branches. So this is an example for the general tree, actually, organizational chart. where you have CEO and then you have so many, different types of designations like chief IT officer, chief of accounts, chief of operations, CFO, COO, you know better the organizational structure. Then you have, I think in Wipro you have verticals. So head will be there and down. So there is some kind of policies or some kind of hierarchy which is maintained, right? For example, this person may report to this person may report to this, because he's in a higher level. So that's why we say the tree structure well suits for this organizational kind of structure. Same thing like family structure, family tree, where you have, parent, then children, grandparents, something like that. So this is what I told, the level need not start from 1 from the root, but it could start from 0 also. And this is the thing, both the left and the right is missing, but still it's a binary tree. Here, left subtree is missing, still it's a binary tree. It's skewed on left. That means totally the right subtree is missing, means absent, so no problem. Still it's a binary tree. So this is very important. Then you have children, parents, siblings, left, right, dissident, depth, all these are usual things, definitions. Some of the other definitions also people talk in terms of tree, the complete binary tree, okay, where you have every node except the leaf nodes should have both left and the right child. That means internal nodes cannot be missing. So that's why it's called complete binary tree. So it becomes very easy to attach some of the properties also to this. For example, 2 power I, where I is the level starting from 0, So 0th level, you will have 2 power I node. So 2 power 0 is 1. 2 power 1, I means the level number. So 2 nodes, 2 power 2, correct? So it's 4 nodes, level number 2. Similarly, you have level number 3. You can see here 4 2s are 8. So level number 3, 2 power 3, which is 8. So if it's a complete binary tree, we can easily say that ith level, you will have 2 power I nodes, something like you can derive. But one problem is if it is not a complete binary tree, then it may not have these properties being satisfied or this formula being satisfied. So that's why we use this word, at most. So instead of level, I call it as D. So if D is mentioned as level, then at each level, it cannot have more than 2 power D nodes. That means you cannot suddenly say that you have one more here, which means that it's wrong. So a full binary tree of height h has so many nodes. 2 power h plus 1 minus 1. So you can cross-check this with some sample data. So additional properties are also there with number of nodes being n, external nodes, all that. And another point to note here is about this. In this course, log is very, very important. And we'll be talking about this especially while we do analysis of certain algorithms, especially when things are mentioned in terms of the tree structure. For instance, if it's a quick sort or merge sort, we use the concept of trees, and in turn, we use the concept of log. Generally, whenever we talk about log, by default, it is base 2. Some books, they don't use log subscript with 2, they simply use lg, which means that it's by default, it is to be understood as that it is log of base 2. Now, generally when we say log, it's log to the base 10. Okay, here it is 2. So why this 2? With figures so that you'll understand easily. So there are additional methods which we have already discussed. These things will be useful in order to construct a binary tree from scratch. For example, you want to, insert. You have inserted, let's take the first node, which is 10 root. I want to insert 20 to the left of 10, correct? Supposing if there is already a node here, okay, 20, I want to insert 30 left of 10, but right of 20. So left of 10, it is not empty, right? So you can check using these kinds of Boolean functions in order to see whether you have any left node or not. Okay, if right node is not there, is null, then you can actually insert this 30 right of this. So like this, you can actually build your own tree depending upon your requirements. Coming to the main part of our discussion. So I told you traversal is the main thing. Traversal, then construction of a binary tree. There are many ways you can construct given a set of nodes with your own methodology. I'll come to that binary search tree later. That is BST. Okay. So it's an order tree. So you fix some order and based upon which you can construct. Or as I said just now, you can construct a tree depending upon the user requirements that a particular node has to be left or right. The third possibility is that again construction. Third possibility is what? You are given some two traversal techniques like in order and pre-order using which you may want to construct. So in the construction itself, you have three ways. OK. This third part, of course, is traversal, then construction, then deletion, which again we will not discuss here later on. So basically, it is a CRUD operation, which is popularly known. Creation, retrieval, updation, and deletion. OK, now let's concentrate on the traversal methods. There are three methods: pre-order, in-order, post-order, just like your expressions. Pre-order means operator will be first, operand next. In-order, operator middle, operands on either side. Post-order, operator, then operands. Similarly here, since the definition of the tree is recursive, so we can traverse through the tree in one of these three ways. So what is pre-order? Okay, pre-order is first visit the root, then recursively go through left and right, because left and right may have a bigger tree, right? A subtree. Means it may have additional nodes, which is again a tree. Right? So visit or print this, then come to this as step number 2, then finish off this, then go to the right. So if I have, let's say, only 3 nodes, so A, B, C, what is my pre-order traversal? It is A, root, then left, then right. Simple. The problem is in this tree, I have very simple subtree, only one node, but I may have many nodes. So follow the same logic. That's all. So even if I have a bigger subtree here with many nodes, I can consider it as with a simple node. Then keep expanding recursively. Next, in order. In order means traverse through the left, then come to the root print, then right. So for this, in order simply means left, come through left, which means B, then print root, that is A, C. So you can see here root appears in between the left and the right. Here root appears first, that is pre. Post order, same thing, like first you have B, then C, then finally A, because root appears at the end. That means traverse through left, traverse through right, step number 2, then finally print the root or visit the root. So visiting or printing appears at the end, in between, and first. So pre, in, and post. Now we'll take this example because earlier I have just shown only one node for the left and the right, but now I have a complicated set of nodes. Okay. So how do we write this? Even if you have many steps, don't worry, it's better to write it to avoid any errors. So here, what is my pre-order? My pre-order is root. I'll consider the left subtree as L and right subtree as R. Done. But problem is L has got many nodes. So what I do, I will break up this into left and the right. So I have a root, left and the right. Okay. So what is my pre-order traversal for this? So I'll call this as X and this as Y. So for L, my pre-order will be BXY. And for my right here, again, I'll call this as my left subtree. And this is my right subtree. So what is my pre-order traversal of this? G. I'm not giving any name. Directly I can write. For this, again, pre is H and I. You want, you can give names also for this. No problem. Now I have to expand X. What is X? It's only one node, so no problem. C. Y is only 3 nodes, so pre-order is D, E, F. So D, E, F. So now if I write this A, B, C, D, E, F, G, H, I. So that's what. Mm, Right. So let's take one more example. Sorry. So we will have some 20. Let me have 7, 11, 9, 6. This time I'm just taking numbers. So 22. I think it's enough. So we want to have the pre-order first. Okay. So now I have left subtree and right subtree. I'll call it as L and R. So 20 L and R. What is L? This one. So pre-order means 7. So this one. Pre-order means root first. Left nothing is there, right full is there. Okay. So I have, let me not write the circle here. I can do that. Just use a different color. Okay, so here there is nothing, empty. And here I have left and the right. Right? So pre-order 7. Left nothing is there. So dash. Right this one. So right I can directly write 6 and 22. 6 and 22. So 7, 6 and 22. So that is done. Now write again pre, that is 11 and 9 direct. So now you can write 20, 7, 6, 22, 11 and 9. So without, one second. Okay, without writing expanded version, in order, for instance, in order is this L, 20 and R. So we can directly write here. For this in order means left nothing is there. So 7. Okay. Left nothing is there, 7, and then this whole thing. This whole thing is 22, 6. So 22 and 6. And 20 is as usual is there, which is my root. Right 9, 11. Because root should come in between left and the right. So now you can see here 7, 22, 6, 20, 9, 11. So like that post order also you can do it. Any example you can take and try. Okay, right. So now We shall move on to how do we represent. We actually represent in two ways. One is implicit or linked. Correct? Implicit means array representation. See, this will be useful when we want to save some memory and linking kind of thing, memory fault, code dumped, all the issues which we have already discussed. We can go in for array, but there are some disadvantages of using arrays also for doing this, but generally linked arrangement is the one which is used. But since most of the modern languages have the predefined packages available like Python or etc., you don't need to deal with pointers. Pointers are also almost removed in most of the lines starting from C#. C++ also you had, but C# onwards, the concept of pointers is there in C#. I have used it. So they advise use pointers only when it is required. It depends upon your application or problem. For example, when you want to work extensively on images, image processing, image analysis, etc., which was my research work. So pointers are very, very fast compared to implicit because these are arrays, so it will take time, but pointers are extremely faster, especially languages like C# and other things. But the problem still, we don't need to actually have pointers, and Python kind of languages, you can just import the appropriate packages so that you can easily use these kinds of data structures, not only data structures, for many libraries like image processing toolbox itself you can have, or you can have some of the complicated software modules itself, which can be imported to your project. In fact, I am also teaching a subject called data engineering, in which we use a data flow or what is known as Apache Airflow, Apache NiFi, etc. with Python. Not NiFi, Airflow uses Python for importing these programs and build a complete what you call the data pipeline in order to monitor several tasks. So Airflow actually gives such facility. I think we'll study another data structure called graph, in which a specialized graph called as DAG, directed acyclic graph, which is extensively used here. So if you look at the applications, there are plenty of, see, what you study here, it will be there throughout. Industry, it is being used, right? It's being used. I have gone to an industry banking sector. Actually, it's a Canadian bank and headquarters in Bangkok, which uses extensively this Airflow kind of thing for building data pipelines. It has got tremendous applications. So, I mean, we can keep on talking about this. Okay, now how do we declare for a binary tree C declaration similar to doubly linked list? Left and right. Of course, info field is there, and you can have your type definition for T node. Whenever you want a variable like P, you can declare it as a T node, tree node. So this is the simplest way by which see, instead of two pointers, self-referential pointers, we can just use one, which happens to be for a linked list. So there are several operations which can be carried out, like we have already seen tree traversal, but I'm going to show you with algorithm and also examples how the recursive algorithms work for a specific example. Then, as I said earlier, creation of the tree. Given two traversals, pre-order and in-order. So we have an algorithm for that. It's a simple logic. Then how do we delete? So we don't show that here, but we will discuss later because we have a separate topic on binary search tree or BST in which this deletion makes sense. Because what we are talking about is a haphazard tree. There is no ordered kind of thing. That means there's no ordering at all. Root any node, children any node. So there is no implicit hierarchy. I mean the values. See, for example, when you say ascending order, you say lower value to higher value or highest value. Descending, first highest, then the lowest. So that's the kind of terminology we use in building an ordered list. Similarly here, when you build a haphazard set of numbers, then there is no ordering. But here it's not, I mean, here it's like that. But later on, we will see how an ordered tree or a BST can be constructed. Then search. How do you search? You can write a simple algorithm given a key, because when it is a general tree, general binary tree, right? That means to completely go through the tree, something like a linear search, right? So you can't, as I've asked you a question, it's not like binary search. Supposing if my key is 5, right? I know that my key is in this portion because it's ordered. Supposing if the key is 25, I know that it is in the right half. How? Because I have the elements which are arranged in a particular order. But in my case here, it's not following any particular order. So searching has to be like linear, start from root, traverse through each and every node until you get so you can write an algorithm. It's an exercise for you. Okay, compute the height, size, total number of leaf nodes, total number of internal nodes, copy or replica, all that. So the simplest one is recursive algorithm for traversal method starting with pre-order. So it's a recursive algorithm. So the first and foremost condition is this one, because recursive algorithm should not end up with indefinite calling. So you should first provide this escape mechanism so that when this condition becomes false, it should come out. No more recursive calls will be enabled. So you start from some root, right? Then visit the root, then take this left link and come to this subtree, left subtree. Then you can go to the right subtree. That's as per the pre-order traversal. So print this and traverse through this. How do you traverse? Recursively. So call the same function, but giving the new address called as the left link address. So this address now will go for this P, right? Then you finish off this. Once you finish off this, once becomes null, it won't call any more recursive call. Then obviously this statement has to be executed. Now you go to the right. So supply this right subtree address to this P. So this is how the recursive, I'll show you this, how this recursive algorithm works on a specific data set. So this is your traversal for pre-order. In order, push this right in between, in order, and that means left and the right. And post order, push this towards the end. So left traversal, right traversal, and then print the root. Okay, so this is the example which I was talking about. So pre-order traversal, these numbers indicate the sequence of execution, right? 1, 2, 3, 4. The last one you can see here, 14th step. And these arrows indicate the way in which the decision is taken. Sorry, the traversal is taken, so that which node it goes to the next. And similarly, these numbers will tell you which statement is executed. So remember, in pre-order, you print the root, then traverse through left with left address. That means left of P. So this is print. Then traverse through right, which means take the right address. Right link address. So print, so 40 is printed and it has to execute this. That means left link is not null. So remember, if P is not null, correct? Null, then only you have to do all this. Left link, actually it is not, sorry, this is P. P is not null. So it comes here, print P of info, which is 40, it's printed. Then take the left address. This is this address. Go to left address means it comes to here. So now P will come here. Correct? Then this is again called the same function. So this goes back. Taking this address, the left address, which means it lands here. Then P is null. No, it's not null. Because it's not null, now it has to print 25. So it prints 25. Next, what happens? After printing, it takes the left address. Which is the left address? That is this one. So P actually moves to the next node here, left. Checks whether it's null. No, it's not null. So it prints 10. You can see here 1, 2, 3, 4, 5, all this sequence. So it prints 10. Right? After printing, it has to take the left address. What is left address? Null. So it goes back to the same function again, taking null. Is it null? Yes. This time it is null. So it won't call recursively. So you can see here left subtree is null. So what it should do? It should go back and execute this statement, which is right. So it takes right address, which is null, goes back. Is it null? Yes, it is null. So it again goes back to 25. 25, it has taken left this statement. Now this is pending for this level. So it comes to the right, taking right address, it comes here. So 32 will be printed after taking the right address, this one. So take the right address, go, not null, print, then again take the left. It is null, so it won't do anything. Right, again null, no. So go back, go back, go back. Anything else is there to print? Nothing is there. So again, return back to the original one. As the first time when it was called, we have gone to the left. Now there is that pending statement is right. So it will come to right. Again, it's not null. So print 78 and take the left address null. So no more recursive. Go back. Take right null. No more recursive. Take go back to the main. So this much work it has to do. Do it for the in order. Okay. Now just go through this, and any doubts you can put it in the chat box. Okay, I think similarly post order. So because this will help you to have a complete tracking of the execution sequence, so that how whatever we have seen earlier, it is only without any recursive things in mind, recursive thinking. Because to understand recursive programs or recursive algorithms, the thinking has to be changed. Because iterative, it's very easy. For I equal to 1 to n or for I equal to 1 to 10. So the statement is going to be executed. That's it. So there is an index variable. But here, many things are hidden. Like, the stack frame is hidden. Return addresses are hidden. That's the stack frame actually. So what are the things put in the stack, so that how does it know that where it should go back, and the levels are, because the same function, we are not calling another function. So all these are very important points, especially when it comes to recursive program execution. So one more exercise for you is try to understand or try to write a pseudocode for tree traversal using iterative method. Got it? So make a note. Assume that in the exam, they ask you to write a pseudocode or an algorithm for tree traversal, let's say pre-order traversal, using iterative method. Okay, so now coming to the construction. So the moral of what I've explained so far is to make sure that don't depend on your other tools, online tools, that tool, this tool. It is only an assistant, or it might give you some idea, but you should have your own strategy, your own method, your own idea to make things work. Okay, it is to create a new node. So this function, and then using this, we'll see how to create some more nodes, but a predefined set of nodes or the tree structure. So this is the self-referential structure. So I have the info field, I have the left and the right link. So I can just use a node, new node construction. And if I don't get the new is an operator which allocates dynamic memory, all that you have studied. So I'll not go into details. And you put the info, that is this one. And then left and the right null. So this is only one node, So this is my data. So this is null, this is also null. Subsequently, I can use the same function now to create some more nodes. So this is what it is shown here. This is the tree structure I want. That is one, left of it 2, right of it, and right of it. So this is the tree structure which I want to build, right? So how do I do it? So create with data 1. So this is the root it has created. Next, n2 equals create data 2. So another individual node. Okay, 1. Then you have 2 separately because each one has got a pointer. This has got a pointer root. This has got a pointer n2. This has got a pointer n3. Right, with 3 as my data. Next, what happens? Root of left to n2. That is this one. And root of right is n3. That is this one. And finally, you can also have n4. That is right of 3. Okay, you can see right of 3 is. This is not good actually. Because you already fixed this. Based upon this, you are trying. It's not a general code. So better way of writing is to ask from the user that any new node, whether you want to be in the left or right of which node, a key node. So you have to search through this, find the key. For example, assume that I have 10, the key node to be added to this tree left of 3. So I input all these things. Key value data is 10 and it should be on left up. So what you should do, you should scan through, traverse through this, find 3. So this is my 3. Next, if it is empty, it's OK. Suppose it's not empty, what will you do? So I've taken a best case scenario or easiest case. So create a new node and left of K, link it with this new node. Done. OK, now I want to create left of 3 again, say 7. But here it is not empty. So you may return as error. So you have to build this logic and then try to create. So take it as an exercise and do it. OK, the last topic for the today's discussion is this. Construction of a, this is very often it is asked in your exam, this one. So that's why I've taken, though it's not mentioned in your regular PPT. Given pre-order and post-order traversals is a reverse engineering. OK, see, generally we have seen that given a tree, write the pre-order post-order. There's one way. Here the other way, given the pre-order post-order, construct the tree. OK. So how do we do it? Very simple. Go to the pre-order, take the first node, make it as the root. Take the next node and refer to in order, depending upon whether it is left of A or right, you have to add this new node. So since B is left of A, you can see here. So add that to the left. Next, you take C and then make it as right of B. You can see here because C appears on the right of B. So that's the algorithm. But you should keep this recursively again. So first node is the pre-order sequence. The subsequent nodes are added to the binary tree, picking them from the pre-order sequence and noting the placement of nodes left or right. OK, in the in order sequence. So you need the help of in order to make sure that where to insert your new node taken from the pre-order. Same thing here. So we'll take an example. This is the full algorithm. So which is the root? A is the root. OK, next B. So where do I insert B? For which I should look into in order. So you can see here A is my root. Now all these nodes actually should appear on the left of A. That's the idea. So now B is on the left of A. So I need to insert here. So B is over. Now take C. C also is left of A, but right up. So this is where the recursive thing comes. So start from root, right? Taking C. You know that C is on left of A, so traverse through the left subtree. And it's not null, but you encounter B. Now you see B, right? So C is actually on the right of B. So my C should come here. So you should satisfy both, like left of A from root and up to my immediate parent. So create X to be then recursive starting from the root up to the most recently added node. That is my B here. Okay. So starting from root, most recently added is B. Got it? Right. Next is D. Okay. So now D is left of A, right of B, and right of C. So it comes here. Next one is E. E is left, all that. Maybe directly I'll come to the most recently added. So E is actually left of D. So it should come here. Next one is F. Okay. F is actually right of D. You can see here. Next G. G is right of A. So here. And H. H is right of A, right of G. So here. Done. Any doubts? Okay, so you can go through this by taking one more example and try yourself. And in case if you have any difficulties, you can raise this question next session. Because take these exercises sincerely and try it yourself. And in case if you have any doubts, you can ask me. Okay, there are two more topics. One is vector representation. That means how to store my tree nodes, children nodes specifically, in an array. So we assume the container here is an array starting from 0 to n-1. Okay, where n is the number of locations. I mean total size. So the children nodes are stored assuming 0, no? 2i plus 1 and 2i plus 2. So this is the formula to use. The left child address is 2i plus 1. Right child address is 2i plus 1. What is I? This is the ith node. So if I have ith node here, my left node, left child will be stored at 2i plus 1. And my right child will be stored at 2i plus 2 in the array. So this is my ith place. So if ith node is at 2, then it will be 5 and 6. That's how the entire arrangement is going to be there. So let's take an example. So this is 0, 1, 2, 3, 4, 5, and 6. Directly we can write like this, but we'll verify. So 2i plus 1. So for example, let's take this node is the ith node. So I is 2. So 2i plus 1 is 5. 2i plus 2 is 6. So you can see here 15 and 47 is stored at 5th and the 6th positions. So 0, 1 and 2. There is 2i plus 1. 2 into I is 0, plus 1 is 1. And similarly, the next one. But supposing if this is not a complete binary tree, then you will have some empty spaces. These are empty, so that's why you get this. So sometimes, it's not a very good way because compactness may not be there. Another interesting application of tree is evaluating your infix expression by building an expression tree. Here, the internal nodes are operators. The external nodes are nothing but the operands. So you can easily evaluate, for example, 5 into 3, 15 is stored here, and 15 plus 2 is 17. Done. Only problem is how to build this tree, expression tree. That's very important. So we have methods for that, which are explained here. But evaluation is easy. All that you need to do is just pop out these operands, that is leaf nodes, and then construct the operation as specified in that node, parent node, star, plus, minus, all that. Keep going. So there's an algorithm for this. You can see here, if it is any operator, then you can pick the children node from the left child address and the right child address and perform the operation depending upon what is in the parent node. That's it.